As we start talking about constructing a confidence interval estimate for a population mean, or estimating a population mean, there are two different cases that we need to consider. Let's start off by recalling that the sample mean, which we represent as x bar, is the point estimate for the population mean, which we represent as mu, which looks like a U with a long tail on that left-hand side. There are two cases to consider when constructing the confidence intervals for the population mean, like we stated. There is the first case where the population standard deviation is known. And there's a second case where the population standard deviation is unknown. If we're dealing with the first case, then what will be happening in the background, Desmos will be handling for us. Confidence intervals will be constructed, calculating probabilities using the normal distribution. And if we're looking at the second case, where the population standard deviation is unknown, probabilities will be getting calculated in the background using the t-distribution. Case 1 is not very practical for real-world applications. It's mathematically accurate and is often looked at, particularly in more math-based stats courses. But for our purposes, we're basically just going to throw out that first case. The readings in our text will cover it. But if the population standard deviation, which is represented as the Greek letter sigma, is unknown, then we'll create our estimates for the population mean using the sample standard deviation, which is represented by S. Unfortunately, S is referred to as a biased estimator, for the population standard deviation. So this increases our error, or increases possible error in our calculations as we construct that interval that we hope contains the true population mean. And that's why we turn to the t-distribution instead of the normal distribution to help minimize our error. Keep in mind the normal distribution and the t-distribution, which here is graphed with 1 degree of freedom, share a lot of similarities, but the t-distribution is both lower and wider. Because of that difference, the intervals that we construct using the t-distribution will be less precise, meaning our intervals will be wider than they would be if we constructed them using the normal distribution. But keep in mind that while we're guessing about an unknown, reducing error is critical. And we want to take advantage of every opportunity that we have to reduce our errors, so that again, these guesses that we're making that are hopefully very informed, very educated guesses, are as reliable and accurate as possible. So creating these wider intervals using the t-distribution means our results will be less precise. But what that's going to do is offset error that could be created due to using S, the sample standard deviation, instead of sigma, the population standard deviation. So we're sacrificing some precision to help reduce error because of this alternate measure that's being used as part of our calculations.